epidemics, but to set the scene, I'm first going to talk about a single SIS epidemic and its behavior. Okay, so first of all, a little motivation. And a little general information about SIS epidemics. So these are one of the main types of epidemics considered by epidemiologists and mathematicians interested in epidemics. So here, every individual in the population is one of the following two types: susceptible or infective. And the idea is that if you become infective and then you recover, you join the susceptible pool again, so you don't acquire any immunity. Okay, and so accordingly, these kinds of models are good for diseases where there's no lasting immunity following recovery, and there are examples of diseases. Now, mathematically, SIS epidemic models are equivalent to so-called contact processes, which have been around in the literature since the 70s. Okay, so give you one simple model of an SIS epidemic that I'm interested in, and that will then generalize to a pair of competing epidemics. So we have a population of size n, and I'm going to be tracking the number xn of t of infected individuals at time t. And the dynamics is as follows. So every infected individual will encounter a random other member of the population at some rate lambda, which is the infection rate. And if the person they meet is currently susceptible, they will become infective. And so the number xn of t will increase by 1 at rate lambda times the number of infectives times the probability that the person you encounter is susceptible, which is the proportion of susceptible people right now at time t. And the second kind of event that can happen is a recovery, and we assume here that every infected person has a independent recovery rate mu. And like I said before, the idea of SIS epidemics is that once you've recovered, you join the pool of susceptibles again. Okay, now there's a very simple deterministic model corresponding to this. So here you can imagine, you can think about it as having an infant population. Before we had a population of size n, which you'd think n being large, that's the case that interests us usually. And here you think of it as having an infant population, and we're looking at x of t, which is the proportion of infected individuals at time t. And again, it's a very similar dynamic. So every infected individual will encounter a random person at rate lambda. If that person is susceptible, they become infective. And again, there are recoveries at rate mu, after which you become susceptible. And you can write down this very simple simple and well-known differential equation for this. And did I skip something? No, I think I'm fine. Okay, so this equation is quite well understood. There are two basic cases. One is when the recovery rate mu is at least as large as the infection rate lambda, and the other one when the recovery rate mu is smaller than the infection rate lambda. So in the first case, the equation has one single attractive fixed point at 0, so all the solutions, all the biologically relevant solutions, which corresponds to x of t, starting with being non-negative and less than or equal to 1, will converge to this fixed point. So the epidemic will die out, okay, in the deterministic case. On the other hand, when the infection rate is large enough, which means in this case bigger than the recovery rate, the point at 0 is no longer attractive. Instead, there's an attractive fixed point at 1 minus mu over lambda. And this time, all the solutions that are biologically relevant, except for the one starting at 0, the trivial one, they all converge to this other fixed point. So that means the epidemic, the state of the epidemic converges to a point sometimes called the carrying capacity of the epidemic. Also, this model actually can be used as a model of so-called metapopulations, and then that would be carrying capacity for some species. Okay, so in fact, it's very simple. You can solve this equation exactly, and the solution is called the logistic curve, except in the case where mu is equal to lambda, and you see that the convergence is exponential to the relevant fixed point, except in that critical case, mu equal to lambda, which is where it's only polynomial. Okay, now coming back to the stochastic model, so we can write down the transitions for the Markov chain I've defined, and then you can work out the drift in the stochastic proportion of infected individuals in a population of size n, and it turns out it's got exactly the same form as the right-hand side of the deterministic differential equation. Okay, now how do the behavior of the stochastic and deterministic models relate to each other? So by very standard methods, if you consider a sequence of these stochastic models, one for each population size n, and you assume some initial condition, let's say initial proportion of infectives converges to some constant, then your the scale, the random proportion of infected individuals will converge to the solution of the differential equation, at least on fixed length time intervals. That's very standard techniques will do that for you. Now, during that kind of interval, fixed length interval, the number of jumps in your random process is typically over order n, and so you might wonder whether you can extend this law of large numbers to longer time intervals, perhaps even until the end of the epidemic. Okay, now, so as for the deterministic model, the key parameter for the stochastic one is the ratio lambda over mu. I call it R0 in keeping with the terminology in epidemiology, and the key is whether this is greater or less than 1. So in the context of epidemic models, this R0 is called the basic reproductive ratio, and it's the number of cases when one case of a disease generates on average over the course of its infectious period. So there's the generic result for epidemics is that if R0 is less than or equal to 1, then the probability of an epidemic becoming established, if you start only with a few infectives, is going to be very small, whereas if R0 is greater than 1, then it's going to remain positive for large populations. Now, in terms of long-term behavior, so the stochastic model is a continuous time Markov chain with a finite state space. So there's an absorbing state at 0, and so by standard theory of Markov chains with probability 1, the Markov chain will always get absorbed. So the epidemic will always die out, even when R0 is greater than 1, just unlike the differential equation. Now what about the extinction time? So at the time, so if I look at the time it takes for the epidemic to become extinct in the stochastic model, then there are different cases to consider. So in the case lambda bigger than mu, or R0 bigger than 1, which is where the differential equation converges to the attractive equilibrium at 1 minus lambda over mu, the time is going to be exponentially large, okay? Now, and you can say more, so you can also say that its distribution is asymptotically exponential. And there's some various work about that in the literature. Now, one can say a bit more, so conditioning on the event that the chain has not yet become extinct, but time t, you can obtain a limiting quasi-stationary distribution, which is centered around this attractive fixed point at 1 minus mu over lambda of the differential equation. So starting from any fixed state, the chain will go very rapidly to be centered around that equilibrium, and will stay there for a very, very long time, and will make excursions, and finally one of these excursions will succeed, and the chain will go extinct. Now, in particular, I don't think that's been done in the literature, but one could show using methods very similar to ones I'm going to discuss here in the context of two epidemics, that the process, the stochastic process will follow the deterministic one for a very, very long time, exponential in n. Okay, now, if lambda is less than mu, so that's the case R0 less than 1, then, like we said in the deterministic model, the population heads very rapidly towards extinction in time on the scale of about 1 over mu minus lambda. And that's mirrored by what happens in the stochastic model, where you have a formula. So what this is saying is that the time t and the extinction basically behaves like the logarithm of the initial condition divided by mu minus lambda plus some smaller terms and plus a random term, which is a Gumbel random variable. Okay, so you can, again, it's more in keeping with how people in epidemiology like to write it. So you can write it in terms of the R0, and there's a speed parameter mu. So surprisingly, that has not been known until very recently. There was an incorrect result in the literature from the 90s, which people just kept referring to for a long time, and so this has been only proven quite recently. It's a preprint joint between me and Graham Brightwell. Okay, now you might wonder what happens in the case in between, the case lambda equal to mu. So it turns out that in this case, the time to extinction is somewhere in between, and in between turns out to be about n to 1/2. Now, but that's not the end of the story, because you understood how you make the transition between the lambda less than mu to lambda bigger than mu via this strange case. So what one does here is to consider a critical window. And so to do the critical window analysis, you need to assume that the rates, the infection and recovery rates, are functions of the population size n. And so it turns out that the critical window corresponds to values of mu and lambda such that the absolute value of the difference between them is bounded by a constant times n to minus 1/2. And there are some results about what happens here. Basically, within this critical window, the time to extinction is like at the critical point, lambda equal to mu. And yeah, there's a fairly precise, sort of nice diffusion approximation for the case where you start close to a constant times n to 1/2 with the number of infectives. And there are some other more general results. So the diffusion approximation is from this 2006 paper, and there are some other results about other starting states in this 2005 paper by Doering and others. Okay, now, so then thinking about this window, you also want to think how you approach the critical window from both above and below. So the case about approaching from above, so when lambda minus mu tends to 0, and in such a way that lambda minus mu times square root of n tends to infinity. So there's the answer is given in the book by Ingemar Nazel, which is dedicated to the logistic model completely, but it's not really proven. He states, he gives lots of results, some of them heuristically, and so this is something that, again, I'm work in progress with Graham Brightwell, again using the kind of techniques I'm going to talk about shortly. And what happens is you can guess the answer by looking at what happens in the supercritical case and just seeing how things approximate as lambda minus mu tends to 0. Now, the case below the threshold, where mu minus lambda tends to 0 in such a way that mu minus lambda times square root of n tends to infinity, that's also covered in that preprint by myself and Graham Brightwell. And again, that just extends the subcritical result, so the formula extends to this case. For the formula of the Gumbel distribution, you need to have the initial state is such that it's of bigger order than 1 over mu minus lambda. It's not that one can't do what happens when it's a bit smaller, it's just that the formula doesn't work with the Gumbel distribution. And yeah, so basically it's just the formula, which is the extension of the subcritical case. So what's the informal description of the behavior? So it turns out that in this regime, if you start at a state quite large, so above about 1 minus R0 times n, then you move very, very fast to the state of order about 1 minus R naught times n. Very fast, meaning faster than the actual order of the extinction time. Now, the bulk of the extinction, of the time to extinction you spend moving from that kind of level to about 1 over 1 minus R naught. And in this case, one can show you follow the differential equation quite closely. And this is a long interval. It's not just interval of constant length, but the length will go to infinity with the population size. Now, most of the randomness of the extinction time comes from the final phase. And when you become small enough, you can ignore the logistic effects and approximate by a linear birth and death chain. So what is there a chalk actually? I just wanted to, yeah. So if you remember the logistic equation, dx by dt equal to lambda minus mu times x minus lambda x squared. So you can ignore logistic effects when this quadratic term is negligible, and that will be when x is much smaller than a lambda minus mu, roughly speaking. And at that point, you can couple the remaining evolution of your process to a linear birth and death chain for which the time to extinction is very well known. Yeah. Okay, so right. So now I'm going to start talking about the competition model. So so here again we have a population of size n, and this time we imagine we're having 2 species or strains of a virus, and I'm going to be tracking the numbers xn1 of t and xn2 of t, which are the number of infective individuals of type 1 and type 2. The dynamics is very similar to what we have in the case of 1 epidemic. So every infected individual of type I will encounter a random other member of the population at its infection rate, which is lambda I. And if the person they meet is susceptible, they will become infective. And so the increase in x and I of t will be by 1 at rate lambda I times number of infectives of that type times the probability the person you meet is susceptible. And then there are recoveries. Again, so here each infective person of type I will recover at its recovery rate mu I and will become susceptible again. So the condition that you only can infect someone if they're currently susceptible means there's a perfect co-similitude between the 2 strains. So if you currently carry strain 2, strain 1 cannot infect you. Okay, so you can write down the transitions for the Markov chain. So it's no longer going to be so easy because the single logistic epidemic is a birth and death chain, and life is a lot easier. Now here we are in 2 dimensions and it's making life harder. Okay, now again you can write down a corresponding deterministic model where you again think of an infinite population where everyone is either susceptible or infected with type 1 or type 2. And I'm interested in xi of t, which is the proportion of the population infected with type I at time t. And you have the same dynamics with meeting someone at and infecting them at rate lambda I times the probability they are susceptible. And their recoveries at rate mu I, yeah, so the same as before. And I can write down a 2-dimensional system of differential equations. Okay, so unfortunately, again, we are out of luck compared to the 1-dimensional model because we don't have an explicit solution to these equations. So that already makes it harder to do things. Now, unfortunately, one can prove various things about them, which are enough for our purposes. So I'm going to introduce 2 quantities, so R01 and R02, which are the respective ratios of the infection rate to the recovery rate. And, oh yeah, and I should say that what's interesting and important is that if one of these strains disappears, then the other one evolves like a single logistic epidemic with its infection and recovery rates. Okay? And so we have these basic reproductive ratios of these 2 strains in the absence of the other. And we're going to be working with the case where one of these strains is strictly stronger than the other one. So say strain 1 is stronger. And we also want this stronger strain to be itself on its own supercritical if it was evolving without the second strain, a supercritical SIS epidemic. Okay, now the differential equations have some fixed points. So, okay, so the first one of these is just there's nothing, both epidemics have gone extinct. The second one corresponds to the stronger strain being at its so-called carrying capacity, the other one being at 0, and so the third one, same, but reverse the rows of 1 and 2. Now, the third one is only biologically meaningful if also the second strain is on its own supercritical. Now, there's a general result of Zeeman, which actually concerns competition model, deterministic competition model for case species, which tells me that the fixed point corresponding to the stronger species is globally attractive. And I'm cheating here slightly because his general result only covers the case where both of them are supercritical. But one can extend this result to cover all the range that I need, which allows also the second strain to be subcritical. Okay, so the meaning of the fact that this middle fixed point is attractive means that the weaker strain will die out and the stronger strain will behave as in the single SIS logistic epidemic model. Okay, now, so with the stochastic model, we consider again a sequence of these models, one for each value of n, and we assume that initial proportions of infectives of the two different types converge to some constants, alpha, beta. I realize this is not the most interesting case. The most interesting case somehow is when the stronger species starts really small and the weaker one will start really big. I mean, we're infecting a fixed proportion of people. So I don't know what happens in this case yet. It's going to be a bit harder because you have to somehow see what happens to get that stronger one out of its initial home, to see whether, under what conditions it will go extinct and under what conditions it can become big. I think I can do this case, but yeah, for the moment this is the easier case that develops some methods. Okay, and right, so like I said, so we focus on that, and so here's a theorem. So the result we've proven is with my former postdoctoral research assistant, who is now Fabio Lopez. He's now works in Chile. So basically, we have proven a result that's along the lines of what's it's similar to, in some sense, to what happens in the single epidemic, or extends that result. So the weaker epidemic will become extinct quite quickly, okay, on the time of the order 1 over the difference between the two reproductive ratios times some logarithmic correction, okay? And there will be again a random fluctuation term, which is again will be asymptotically Gumbel distribution. Okay, so this weaker strain will go extinct quite quickly, and so afterwards, after this logarithmic time passes by, the stronger strain will be left alone and will behave like a supercritical logistic epidemic, and therefore the result for the single supercritical logistic epidemic will apply, because this initial time we waste, so to speak, is so insignificant. It's still in this little O1 correction, so it doesn't make a difference. Okay, so that's the result. And okay, and similarly to the single logistic epidemic, there will be a phase where the scaled process, so here scaled process will be two-dimensional. It will be a vector whose first component is proportion of infectives of type 1 and second proportion of infectives of type 2. So we can show that there will be a phase where it follows the differential equation quite closely. And then again, there will be this phase where by which this proportion of infectives of type 2 will become quite small. And then you can ignore these quadratic effects in the drifts and approximate subsequent evolution by a linear birth and death chain. And you can figure out what the sort of corrected infection, or the corrected birth rate, so to speak, for this approximating birth and death chain would be. Okay? And yeah, and like I said, so far we have only looked at this case where you start with positive proportions asymptotically of both types, but future work will consider other starting conditions. Now, we also have started looking at what happens the near critical case. So again, near critical approaching. So the critical case here corresponds to where the two basic reproductive ratios are equal, or where the stronger one can equals to 1. Okay, and I've told you about sort of near critical behavior for the single epidemic model. Probably I should have given you that justification a bit earlier. So why is it interesting from any practical point of view, for example? So it can be important for when you look at emerging diseases. So, for example, you've got some 2 strains, and then there's a mutation in one strain, which can move its basic reproductive ratio across the threshold, where it is capable of causing a big epidemic. Okay, and so this is why generally it may be interesting. And so for our, like I said, for our model, it could be either where the stronger one becomes, has its basic reproductive ratio closer and closer to 1, or the difference between the 2 basic reproductive ratios becomes close to 0. And there are lots of possibilities, and it's quite the reason why it's difficult is again because we don't understand what the differential equation does. We don't have an explicit solution. So far we have only looked at a very special case where infection and recovery rate, where the 2 recovery rates are the same, and we're looking at lambda 1 and lambda 2, the infection rates both being bigger than 1, and lambda 1 minus lambda 2 tends to 0, but in such a way that it's much smaller than lambda 1 minus 1. Okay, so that means the difference between the 2 basic reproductive ratios is much smaller than the difference between the stronger basic reproductive ratio and 1. Okay, so this could, for instance, model the case where a slightly more infective strain emerges by mutation. They both cause disease with roughly similar infectious periods. And now we want to know how long it would take for this new strain to supplant the weaker one in the population. Okay, and we can, it turns out in this case, we can, under some sort of assumptions. So if you look at this third assumption, it's very much analogous to the single epidemic, a single logistic epidemic where I wanted n times lambda minus mu squared to tend to infinity. I just need some logarithmic separation here. And the same, the one above, it's kind of similar for the slightly bigger quantity, lambda 1 minus 1, and I need a slightly lesser separation. And then there's another sort of related condition at the top. And basically then the formula extends, the formula we had in the case bounded away from criticality. Okay, so now I want to tell you about the proof. For simpler computation, the computations become a bit complicated. So to make them simpler, we just did them in the case where the recovery rates are indeed equal, and we allow arbitrary infection rates with the condition that the strain 1 is stronger, so lambda 1 is bigger than lambda 2, and strain 1 is supercritical, so lambda 1 is bigger than 1. And I need this, for the case I'm considering, I'm assuming that this quantity A is not equal to 0. The reason I'm assuming it is because under that condition, some matrix that will come up quite shortly doesn't have repeated eigenvalues. One can do it, the case where A is equal to 0 as well, but the computations are a bit different, and so I'll just focus on this one case. Okay, so what we do is start quite standard. So I'm going to write my solution to differential equation as the initial condition plus the integral of the drift. And now we're going to really look at, so the second component will converge to 0, but the first component will converge to this other quantity, which in this case is lambda 1 minus 1 over lambda 1, it's the carrying capacity. And so I'm going to be working centered around that the fixed point lambda 1 minus 1 over lambda 1, 0. So we're going to decompose the drift into a linear part and a non-linear part. And this is where the simplification helps, because the eigenvalues of this matrix become, not really, the eigenvalues are simpler in this case than they would be in the general case, and the computation of other things becomes simpler. As well as, not to mention the quadratic corrections. I mean, in the future we hope to develop a generalization of this method, but this will become unimportant, but for the moment it's just good to calculate explicitly. Okay, so this case A equal to, A not equal to 0 means that matrix A here has distinct eigenvalues. And then one can check that we can sort of re-express the formula using the exponential of this matrix A. So we can write the solution at time t as the initial condition times e to t times exponential of the matrix A, and plus the integral of the, basically the convolution of this non-linear part, again with this exponential of this matrix A. And one can calculate this exponential matrix. Okay, so we do this, and then, so first of all, what I can gain from, and that representation helps me quite simply prove everything I want about the speed of convergence of differential equation to the fixed point. I told you the general theorem didn't cover all the cases I wanted, and here I'm able to prove, to cover the rest of the range. So we have that, and we have the decay of the solution to the differential equation to the fixed point we want at an exponential rate. Now, next thing we do is we want to show that the stochastic process, the scaled stochastic process, so we work with the proportions of the infectives, tracks the deterministic one for a long period of time. And so we're going to proceed very similarly. So we're going to write the state at time t as the state at time 0, plus the integral of the drift, and plus a martingale. And it turns out we can decompose in the same way using the decomposition of the drift into linear and non-linear part, and we just end up with a slightly awkward term at the end, which is no longer a martingale, but a martingale transform of a kind. Okay, and so how do we deal with this? So we need to show that the stochastic process follows the deterministic one. We need to deal with that term. So it turns out if I fix any time tau, and I define a family of martingales indexed by this tau, well, all I do is just replace the t in the exponential by tau, okay, and I stop the martingale at time tau. And that's going to be a 0 mean martingale. And then it turns out one can bound the quadratic variation of this martingale and then show that the transform I'm interested in behaves well, small with high probability. But because I have a whole family of these martingales, one for each time, so what really needs to happen is that we look at a set of discrete times and then argue that nothing much can happen in between these discrete times. Okay, so that's what we do, and then one can use this to bound the differences between the stochastic, the first component of the stochastic process scaled, and the deterministic one, and likewise for the second one, with high probability over a period of time, which we make deterministic, and we stop at the point where the second component of the differential equation becomes quite small, small enough that we can ignore the quadratic effects. And at this point, we can show that the first component will be quite close to the first component of the fixed point as well. Now, so this is in essence what we do. Now, actually, for yet simpler calculations, it's easier, at least in the case where this quantity A is not equal to 0, so the eigenvalues are distinct, to work with the new variables, which correspond to the eigenvectors of the matrix A. Okay, so we keep the second component as it was before, but the first component is a linear combination of the original first and second component. And actually then life is a bit simpler. So first of all, you can re-express the differential equation in the new variables. And now the linear part is going to be diagonal. And so that makes life better. So you can do this, actually you can do the same decomposition as I've done before, but it's simpler because my new matrix A tilde will be diagonal, and so it'll be easier to calculate its exponential. And the quadratic errors are not really much worse than they were before. And so you can write down the same thing as before, but with these new variables for the deterministic solution. And then it's so actually you can prove again what I said about the convergence to the fixed point. And one thing that I also need to have a lower bound on how fast we converge, because that enables me that enables me to deduce that the first component is also going to be how I want it to be. So you prove this lower bound with speed of convergence as well. And
so how do you actually prove these strong convergence results? So it's not just Grunwald, right? You need to do something.
I do what, sorry?
It's not just Grunwald. You need to do some much.
Do
more.
what? Not
like
just.
some Grunwald type.
I do actually use Grunwald, but I do use Grunwald with not sort of the function itself, but multiplied by e to t some constant, which is like the smaller of the eigenvalues. Yeah. So I'll get to something similar to that, but in a moment. Yeah, so you can do the same for the stochastic process, and again, what it makes it easy is that the martingale bits are now have the diagonal form as well, so that makes it easy to get the martingale deviations. And oh yes, and to get the bounds on so I've told you there's this family of martingales indexed by each time t that I have, and it turns out you can in fact, it's not completely obvious a priori, but the quadratic deviations can be calculated indeed just using what you would expect to use, so to speak. So using the integral until time t of the rate of events times the not the jump squared, but the jump multiplied by your matrix exponential squared, and that gives you the right bounds. And so when you can show us that while these quadratic variations are not too large, then you can show that your martingale transforms can't get very big. So this extra e2 beta I that you maybe wouldn't expect if you were just doing the standard thing is from the fact that you have to have these discrete times you work with, and then you have to say what happens between discrete times. Okay, and then so once you've done that, you consider the maximum of the difference between the stochastic and the deterministic components, first and second. I throw in this constant there just for neater computation, no particular purpose. And then you are able to show that if you start not too big, say no more than 1 over square root of n times some corrections, then over a very long interval, I mean, this omega you could choose almost as large as over the n. So over a very long interval, you're going to be still quite small, okay, with high probability. And how you do that? So the idea is that when you collect all your terms in these equations with the transforms, you're going to come up with an inequality of this form, that the maximum of the differences between the two components is at most the initial thing times E2 minus t times L, where L is the minimum of the two eigenvalues. And then you have going to have a second term which involves the integral of this Fn itself, and you've got the last term which is like a martingale term. It's on some good event. So the good event is that the martingale deviations are not too large, or the martingale transform terms are not too large, and you need some very weak bound on your FNT, which is much bigger than what you're actually trying to prove. And then you come up with this, and then you can apply Gonwa's inequality to deduce what you need. Yeah. And yeah, and so for a suitable choice of omega, the time Tn, which is you want time Tn, was defined as the time when the second component of the differential equation drops to n to minus a quarter. N to minus a quarter is a bit arbitrary. I could have n to minus a third or something like that. And so at that point, the vector, the deterministic vector is very close to the fixed point, and hence the stochastic process is also close to the fixed point. And then you can do, again, coupling of the second component with a linear birth and death chain, and closely approximate the time to extinction from now on by that of a linear birth and death chain. And then the total time, so first you've got this, so this first term, I've got two terms. The first one comes from the differential equation. So actually one thing one can prove about the system of two equations is that if I want to move from point AB to point CD, where both lie on the curve of the equation, then the time to do so will be lambda 2 over lambda 1 minus lambda 2 times log of C over A minus lambda 1 over lambda 1 minus lambda 2 times log of D over B. And so that will be the time from the differential equation. And then the second phase is from the coupling with linear birth and death chain, where one can use standard formula. And
so can both of these be of the same order of magnitude? The Gumbel variation, of course, is smaller than the
yes,
the
Gumbel,
constant term
yes.
here. But the first and second one
so this so what happens is that actually this there's a cancellation happening here. So this x2 of Tn,
yes,
so the differential equation will cancel with that bit. So you're really going to be left with lambda 1 over lambda 1 minus lambda 2 times log n. And then from the first term, this log of so x1 of t n is like lambda 1 minus 1 over lambda 1. So here at the moment we are sort of in a non-critical regime. So the answer is, I think this second one is longer.
Okay.
Yeah. Yeah. Now in the near critical case, things get more complicated. That's why we only looked at really one regime. So here it becomes necessary to break the analysis into three phases. So the last phase again will be just a coupling with a linear birth and death chain. Now the first two phases will be again an approximation of the random process by deterministic, but you have to do them separately because to get the right precision you need to use different bounds and the quadratic variation terms for each phase. So the first phase will correspond to the case where both your components start constant, and then so in this, so when you move to new variables, they both go to 0. Okay, so you're starting with both of them constant, and then in the first phase, this is the first eigenvector corresponding to the eigenvalue lambda 1 minus 1, which in this case is the lambda 1 minus 1 is bigger than lambda 1 minus lambda 2 over lambda 1. And so that's the minus lambda 1 minus 1 is the eigenvalue further away from 0. So this is going to be converging first. And after some time of order about lambda 1 minus 1 inverse, will fall to about delta times lambda 1 minus 1. And then, so you do that phase separately with sort of fairly weak bounds on the quadratic variation. And then you start a bit smaller in the second phase and you work for then quite a long time, and as long as you need for this second scaled component to drop below lambda 1 minus lambda 2, which is the analog in the of this getting below lambda minus mu for a single epidemic. And yeah, and that happens on the scale on the order of time of all the 1 over lambda 1 minus lambda 2, which is the corresponding to the eigenvalue near 0. Okay, and then finally you have this phase again with the linear depth and left chain. Okay, and future work, so different starting conditions, more relevant for practical uses, and different near critical regimes. So where, for example, where the two eigenvalues are of the same order, that would be an interesting different regime. General number of case species, okay, and generalizing the method would be very interesting for us to write down a general version of the method that will work for other processes of this type. And I think that's it. So thank you for your attention.
Do you have any questions for Malwina?
Yes.
I misunderstood. But did you say that if R1, R01 is bigger than R02 and R02 is bigger than 1,
Yes.
then the second species dies out?
Yeah.
Faster than the first species?
Yes. So even though both of them can be supercritical, but the second species will still die out.
So you've got an intuitive explanation for that?
I think the reason is that they compete for the susceptibles in the pool of all people because of the cross immunity, and so the stronger one is sort of more greedy. So will take
It's not like they take over all the susceptibles, are they? I mean, they're sort of some kind of equilibrium, so there's still plenty of susceptibles.
Yeah, but not enough.
I think the way I see, I mean, I didn't do a calculation, but the way I see it is that in the stationary state, you have a fixed proportion which are susceptible, fixed proportion which has the stronger one
Exactly.
and the weak one. But that means that the ones which are infected by the stronger one, they make up a large proportion. So what is left? If you just look from point of view of the weaker one, that means that effectively you have a smaller population,
Exactly.
which means that effectively you get a smaller R naught.
Yeah, exactly.
It always gets pushed down to less than
Yes,
1.
Yes,
that will be-
exactly. Yeah.
Yes, because I think that for the stronger one, it will, since it is a steady state, must
Yes.
be that the effective R naught for the strong one is
Yes.
equal to 1, and therefore it has to be strictly less than 1 for the weaker.
Yes. Yeah.
And therefore that will die out long before the strong one will leave it.
Exactly.
Quasi-stationary
Exactly.
And this would be used for sort of public health. Introduce a milder form of the disease that makes you immune to this.
Yeah, did you
form
hear?
of the disease.
Possibly.
Was it that what Jennings did with the
Yeah, that's
smallpox, cowpox?
This is what it's done.
Yeah, probably.
Right, so there's usual theories to 200 years ago.
No, that's a good point. Yeah, indeed. Yes.
What do you think will change when you have more species? Is it just going to be one species and others who are not?
To be honest, I'm not really sure because I know that the differential equations can get worse the higher dimensions you get. 2 dimensions, I think, are still quite mild. Once you get to 3, then I'm not totally sure what will happen. I hope not very much will change. I hope you can still do it, but I'm not absolutely sure because we don't really understand the differential equation yet.
Do you imagine that you might have complicated situations where you might be competing or not? So if you have like 10 species, then maybe you could be susceptible to species 1.
I don't really know. I don't really believe that anything really strange happens.
Okay.
No, it's just that I'm not totally confident because I realize I'm not an expert on differential equations and I know they get worse in higher dimensions.
Yes.
So I actually have 2 questions. So one is, what have you considered the effect of competition between the two? I mean, that you could have this cross-immunization effect. I mean, in some sense, I'm not an expert of biology, but if you already have a disease, maybe it's more likely that the other guy will take over or jump to it.
So you mean then that you could infect even if you're already infected?
Yeah,
with...
that maybe go from 1 to 2 or vice versa. Will this?
No, we haven't. I imagine it will be a very different type of model. So you won't have this property of reducing to a single SIS epidemic once you remove the other species. And I think that's important, at least for this formula, the intuitions to carry over. I mean, in principle, I think the method is really hopefully quite generic, but you could really consider any family of Markov chains when there is some attractive equilibrium, then you would hope you can carry out a similar approximation, but I'm just not sure whether the answers will be the same with Gumbel distribution and so on, because I don't quite understand how that would behave.
So one more question maybe. So when you analyze the process, it seems to be pretty important that everything is sort of linear, that you have these linear terms in the differential equation.
But you can always have linear terms in the differential equation. So when you have a fixed point, you can always linearize around the fixed point, and then you have some junk, which is going to be quite small, hopefully. But this is why we haven't tried to do general to begin with, because you just have to worry a little bit what happens when you have to have more than just quadratic terms in the Taylor expansion. But yeah, you can always linearize.
So is it clear that the linearization will always give you a good approximation?
Well, if you have an attractive equilibrium, the linearization around the fixed point will have negative
Okay, so
eigenvalues.
that's the key point, that you have
Yes,
this really attractive.
exactly. You have negative eigenvalues. Yeah.
Questions? Okay, Malvina, okay.